Hello everyone, this is Rashika Janjarla. I'm an educator in Unacademy. You can follow me on Unacademy learning app where you can find other courses as well. In this lecture, you are going to see the nipping of leaf springs. And please rate, review and share the video and also subscribe to Unacademy YouTube channel. Welcome again to nipping of leaf springs. In the last lecture, we have discussed about the design analysis of the portions of the multi-leaf springs, right? They are the graduated length portion and also the extra full length leaves portion, and we have calculated the bending stress values and also the deflections of the portions of the multi-leaf springs, right? So here we have the bending stress in graduated length leaves given by sigma bg equals to 12 pl by 3nf plus 2ng into bt square, right? And the bending in the full bending stress in the full length leaves of the multi-leaf spring is given by sigma bf equals to 18 pl by 3nf plus 2ng into bt square. So on observing these two equations, you can find that the bending stresses in full length leaves are 50% more than those of graduated length leaves. So it is better to keep these two stress values equal for the multi-leaf springs to have a common strength value. So now we are going to discuss about one of the process to make these two values equal, these two stress values equal. Okay, so the process is called as nipping, and we are going to discuss about it now. So the nipping, one of the methods equalizing the two stresses in different leaves is to pre-stress the spring. The pre-stressing is achieved by bending the leaves to different radii of curvature before they are assembled with the center clip. See in this figure, here we have the extra full length leaves and the adjacent leaf of this extra full length leaves. Okay, so the curvature, radius of curvature of the extra full length leaves is greater than the radius of curvature of the adjacent leaf. Okay, therefore the pre-stresses developed in the extra full length leaves are lesser than the stresses developed in the graduated or the adjacent leaf of this extra full length leaves, right? So as I said before, the stresses in the extra full length leaves are higher, right? Higher than the graduated length leaves. Here, on bending the graduated length to a curvature which is higher than the curvature of the adjacent leaf of this multi-leaf spring, the stresses will be balanced, right? Therefore we can say that the stresses in the extra full length leaves and the adjacent leaves are equal, because the bending stress causes the bending loading acting on these two spring leaves causes more higher stresses in the adjacent spring than the stresses in the extra full length leaves. So when this spring undergoes some external load, the stresses produced in the adjacent leaves are lower than the stresses developed in the extra full length leaves. As I said before, the stresses in these two leaves of the multi-leaf springs are balanced then. So we have to pre-stress the spring before the service. So on assembling these leaves of the multi-leaf springs, we have to apply some bending loading, and we have to apply some bending loading, and we have to create some pre-stress in these leaves. Okay, as you can see in this figure, the radius of curvature of the full length leaves is greater than the adjacent leaf. The radius of curvature decreases for shorter length leaves, because on decreasing the radius of curvature, the stresses in the leaves of the springs is increased, right? And when they undergo service, the stresses developing on those leaves are lesser than that of the leaves which has more length. Okay, therefore there at the surface, the stresses in these leaves of the springs are balanced and they will be equal. So this is the process to achieve the same bending stress values in the leaves of the multi-leaf springs. Okay, the initial gap C between the extra full length leaf and the graduated length leaf before the assembly is called nip. So as I said, so these two leaves of the multi-leaf spring has different radius of curvature, and the distance between the two leaves is given by C, and it is called as the nip of the multi-leaf springs. Okay, and it is achieved by pre-stressing in the leaves of the spring by the application of a bending load. Okay, so such pre-stressing achieved by different radii of in curvature, and this process is known as nipping. Okay, so this overall process is known as the nipping, which is used to make the stresses in the leaves of the spring, in all leaves of the springs, equal. So design analysis of nipping in leaf springs. Okay, so we have the relation for the bending stresses given by these two relations, as I said in the introduction of this lecture, right? So in nipping process, what happens, the stresses becomes equal. The stresses in the graduated length and also the stresses in the full length leaves are equal. Therefore we have the relation sigma bf equals to sigma b into g, right? So from this equation we can get the values pg by pf equals to ng by nf, that, and also we have p equals to pf plus pg, right? And so on solving this equation we get the value of pf equals to nf into p by n, and pg equals to ng into p by n, and n equals to ng plus nf. And also we have the equation for the deflections given by delta g equals to 6bgl cube by eng bt cube, and delta f, the deflections in the extra full length leaves of the multi-leaf spring, given by 4pfl cube by enf bt cube, right? Under the maximum load P, the deflections of graduated length leaves will exceed the deflections of extra full length leaves by an amount equal to the initial nip. See, right? So here in this figure you can see the deflections of the extra full length leaves and the graduated length leaves is the difference between the deflections of these two leaves of the multi-leaf springs is C, right? So this is the gap, the nip of the multi-leaf springs. So the gap C will be, the nip C will be C equals to 6pgl cube by eng bt cube minus 4pf l cube by enf bt cube, that is delta g minus delta f. Okay, on solving for C we have got the value of C equals to 2pl cube by en bt cube. So this is the nip of the multi-leaf springs which is under the application of nipping. Okay, so force required to close the nip gap. So now we are going to see how much amount of force to be applied on those multi-leaf springs to close the nip gap of the multi-leaf springs. Okay, so the initial preload required to close the gap C between the extra full length leaves and the graduated length leaves is determined by considering the initial deflection of the leaves. So under the action of preload Pi, we have C equals to delta Gi and delta Ft I, where I, the subscript, tells us the initial preload applying on the leaves of the multi-leaf spring. So due to the application of that pre-stress or the preload on those leaves, they undergone a deflection of delta G, and the extra full length leaves undergone a deflection of delta Fi. Okay, so on substituting these values we have got the value of P1 Pi, or the initial preload that should be applied on the leaves of the multi-leaf springs to close the nip gap, that is given by Pi equals to 2nf ng into P by n into 3nf plus 2ng. So this is the value of the force required to close the nip gap, denoted by C. So this equation is important, and also the nip formula, and also the stresses, and also the deflections in the portions of the multi-leaf spring. Okay, so the resultant stresses in the leaves here. So the resultant stresses in the extra full length leaves is obtained by superimposing the stresses due to initial preload Pi and the external force P. So the extra full length leaves are under the application of preload and also the load at the surface, that is the external load P, right? And the portion of load taken by the extra full length leaves of the multi-leaf spring is Pf, right? So therefore we have sigma B equals to the stress caused by the preload and also the stress caused by the external load, and also the Pf, right? So we have 6L into Pf minus 0.5 Pi by Nf Bt square. Here Pi, 0.Pi is the half of the preload, because this preload is shared by the graduated length leaves and also the extra full length leaves, right? That's why we have half of the preload. That's why here in the place of the loading we have Pf minus Pi by F, and there the stresses are in the opposite direction. That's why we have got Pf minus of Pi by 2, that is 0.5 Pi by NF BT square. This is the stress, the bending stress developed in the extra full length leaf portion of the multi-leaf springs when it is under the application of the preload or the process of nipping. Okay, so from this we have the preload given by Pi equals to 2NF NGP by N into 3NF plus 2NG, right? So on substituting this value in the above equation for sigma BF, we have got the value of the bending stress in the extra full length leaves of the multi-leaf spring given by sigma B equals to 6PL by NB T square. So this is the value of the resultant stresses in the extra full length leaves of the multi-leaf spring. Thank you.